Okay, so the previous video I talked about how heat spontaneously flows from hot to cold, and the second law says that we can't convert everything into work. Well, what we can do is convert some of it into work, and that's where the Carnot cycle comes in. And the Carnot cycle is a great way for us to identify what entropy actually is and quantify it. So not only did I name my cat Carnot because this person is awesome, but this is really the definition of, at least the thermodynamic definition of entropy. So if we have a pressure and volume curve, so that would be an isotherm. So this is at T, I'm going to say hot. Okay, so this is the hot temperature. Another isotherm could be at a colder temperature. So if the temperature is colder, we're going to say T cold. All right. So then what I can do is I can have my process go from this volume and this pressure down the isotherm following the ideal gas law to this value. And then what I can do, actually I'll go to this value. So this would be an adiabatic transfer. So where T changes, but Q equals 0. And likewise, I can come back then and it go along the adiabat to this point and then come back up T cold until I hit another adiabat and then get back up to my initial point. This creates the cycle. I'm going to switch over to an animation to really help you get this picture in your mind. Okay, I'll post this link on Moodle, but it's really great for you to see this in action. So we have an isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Those 4 steps added together give us a complete cycle. So we started at a high pressure that causes the volume to expand. Now we're adiabatic expansion, no heat's transferred, but we're changing temperatures. Now we're at an isothermal compression. This is at T cold. And so as we compress, the pressure starts to get bigger, but notice no temperature is being exchanged. Now at an adiabatic compression, we're going to have no heat exchange, but there's going to be a massive temperature change, as well as a pressure and volume change. And so heat naturally flows from hot to cold. And so there is a spontaneous aspect of the expansion because you're of the adiabatic expansion, because that's where you're natural or spontaneously getting the system to go from the hot system to the cold system. No heat exchange during that time, hence the adiabat. So now low temperature, heat is dumped. So there's going to be some heat loss, and that heat is what doesn't go into the temperature change. It has to go somewhere, and it's not going into changing the temperature. Likewise, so when heat's being pulled out of the system, you're going to have no temperature change. But under the adiabatic expansion or compression, no heat exchange, the heat's going into the change in temperature. Hence, you're getting back up to that T hot isotherm. Cool. So the piston keeps going, and this is how we extract useful work energy, or we convert heat energy into useful work energy. And that heat is that we're extracting out. See if you can figure out where we're gaining that heat. That heat's coming out of our engine. And it's also interesting to think about how is heat supplied. Give you a hint. It's a combustion engine. So for a steam engine. So as you're applying that heat, that has to come from some sort of fuel. And so heat in, convert it to work. Heat out, use that work. Cool. Okay, back to the Carnot cycle. Okay, so you're going to go through the Carnot cycle on your own, or possibly in groups, but I just want to give you a sense of what it is, the mathematics behind it. So you've got volume 1, 2, 3, and 4 at the different points. And again, this is very expanded so you can see it. The curve that you saw on the animation is a lot more appropriate because isotherms are going to be very steep, but then adiabats are even steeper. So this is not drawn to scale. So anytime you have an isotherm, that means delta T is 0. Well, delta U is equal to CV delta T. That's great. That goes to 0. Hooray. Well, if that's the case, that means Q is equal to minus W. So then, because you have a reversible isothermal expansion, you should then be able to determine what your work is going to be, which is going to be the same as your heat, except for a negative sign, which I believe is going to be minus R, what is that, RT log V, who's that, V2 over V1. But you should be able to derive that. And this is going to be T hot, so the hot temperature. Then here, adiabatic, the process 2. So that's Q is going to be 0, which means our delta U is going to be equal to W. And then our work associated with this is going to be, so delta U is going to be CV delta T, which means that our work is then heat capacity multiplied by our change in temperature. And then likewise, isotherm, delta U or delta T is equal to 0, which means delta U is equal to 0, Q is equal to minus W. But now we're going backwards because instead of it being V2 over V1, now we've got V4 over V3, but V4 is smaller than V3, so you're going to have a change in the negative sign. Likewise here, going back from V4 to V1, this is where we complete the cycle. It's another adiabat. So we've got Q is equal to 0 and delta U is equal to W. So in this, if you add up all of these processes, process 1, 2, 3, and 4, you should then get the change in the work, or sorry, the change in the internal energy for the entire system. So delta U total would then equal the sum of delta U1 plus delta U2 plus delta U3 plus delta U4. Okay, so adding each cycle to adding each step together will then give you the total of the system because we're dealing with state functions, not dealing with the inexact differentials. Now we're going to talk about the efficiency of the Carnot cycle, and the efficiency is going to be equal to what you get out divided by what you put in. So that's essentially the idea of efficiency. You're going to put something in, and if you get all of it back out, 100% efficiency. What you get out is equal to what you put in. Again, not the case. But we can convert this then. So the efficiency is typically the fancy N with a little tail. This is eta, the Greek letter. And so we would represent this as the what we get out would be the work. And I'm going to put this into absolute value. So we're getting the magnitude of the work divided by the heat that we put in to the system from specifically the hot reservoir. Because again, once we're going to lose some heat energy, or there's going to be heat energy associated with the loss as it transfers from the hot body to the cold body, or the hot reservoir to the cold reservoir, but we're specifically looking at the heat that's coming from the hot reservoir. Okay, you can also look at this as the work done by the system, because again, that's a negative, that's going to be what's given off, and that's what work energy we have now converted from the heat that we put in. And then this is heat added to the system. So to the system from T hot reservoir. Okay. And what we can do then is, and actually I'm not going to show you the steps. Well, it's a video. I can totally show you the steps. So eta is equal to minus W over Q. And so from the work done by the system in this case is going to be RTH minus TC, the difference in the temperatures, log V2 over V1. So then this work comes from adding up all of the different works associated with the overall cycle that the system has done. So work 1 plus work 2 plus work 3 plus work 4 from the cycle that I just showed you, you add all those up, and this is where you get this relationship. So then you want to know the heat that comes from the hot reservoir. That is going to be equal to R times T hot log V2 over V1. And so you do some simplifications. Your R's cancel, your logs cancel, and you're left with TH minus TC over TH, which gives you 1 minus TC over TH. And this is typically the relationship that you'd see for an efficiency of a Carnot engine. And something that's really interesting about this, think about what it means to be 100% efficient. That means eta is equal to 1. If eta is equal to 1 minus TC over TH, how can this be true? I won't even answer that. I'll let you think about that. But how can you get this to equal 1, this relationship to equal 1? And what does that physically mean? Go team. And I think that's all I want to talk about with efficiencies of Carnot cycles. The next video will be relating all of this to the definition of entropy.